we have seen the basic idea of how to do discretization using the finite volume approach for the same equation as what we had seen earlier. Now in this lecture we will actually go through the fine detail of this and see how we can use the finite volume method to write an equivalent expression for the partial differential equation in a cell. We go back to the example of the triangular duct. So we go to the triangular duct here. For the sake of convenience, we are taking an equilateral triangle and we split this up into equilateral triangles like this. We can identify the centroids. We mentioned that these are 2/3 of the height from the top and 1/3 of the height from here. So they will be like this. We can also, for our sake, number these cells as cell number 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, we are doing this approximately for this. When we do a tutorial on this, then we can do it with much more clarity. In this lecture, we are going to look at, for example, cell 7 only, and then try to convert this partial differential equation into an algebraic equation. Okay, and the way that we said that we do this is to write this as del dot del W equal to C and integrate it over the area of cell 7. For example, we do this, and this is equal to C times, and because this is over a closed area of this cell, we can write this as integral of n dot gradient of W dl along the sides of cell 7, and this is equal to C times area of the cell 7. Okay. So now we would like to discretize this further, and for that we need to identify the cell 7. This is our cell 7. It has a centroid here and it has, as a neighboring cells, we have cell 9 here with a centroid, and then on this side we have cell 6 with a centroid here, and on this side we have cell 8 here with a centroid here. Okay, so this is our cell, and we have identified the 3 immediate neighbors with which it is sharing a face. For example, this space is being shared by 7 and 9, and this space is being shared by 7 and 6. This is being shared by 7 and 8. Let us also put some names for the vertices so that we have, it's easy for us to follow, and we have these ABC here. These centroids can be determined. Okay, so we know we denote by XC and YC are the X and Y coordinates of the centroid. Centroid of cell I. For the ith cell, we have XCI and YCI as the coordinates, and therefore we know the centroids of cell 6, cell 7, cell 7, cell 8 and cell 9. So these are known from the geometry and layout of this. And so now with this thing we can apply this equation as for cell 7, we can write that equation as n dot gradient of W over times L of AB plus n dot gradient of W times L over side BC plus n dot gradient of W times L over side CA is equal to C times area of cell 7. Okay. So from the known x, y, z's of coordinates of the 3 vertices, we can evaluate the area, and so in a way that's straightforward. Also given that it's an equilateral triangle, we can readily find that out. So now what do we do with this? Now if you, this is n dot, so ideally this should be integral along the length, but given we are looking at CFD and where the cell size are supposed to be small here, and we are associating with each cell a node which only at this node we are evaluating the variable W. So we say that integral of this along a particular side is approximately equal to the evaluation of this at the center of this. Okay. So for example, if you know, so we are saying that along side AB is approximately equal to n dot gradient at the midpoint, which we can call as, for example, P here, and the midpoint of this as Q and this as R. So evaluated at P times LAB, where L is the length of the side AB here. Okay, so we are making this approximation, and now it's a question of, so using this approximation here, we can write this thing as gradient at P times LAB n dot Q times LBC R times LCA equal to C times area of cell 7. Okay. So the reason why we explicitly wrote up like this is that in order to evaluate these gradients and the surface normal vector at P, we need to know the xy coordinates of P, Q and R. Okay. So we also need to know x and y coordinates of P, Q and R for cell 7. We will see why that is needed, and that can be worked out from the geometry. So all the geometric information related to this, what is the length, what is the area, where is the centroid, where are the center points of each side, all that thing is to be is essentially known from the geometry. So now if you are looking at at point P here, we can write this as the x component of the normal vector plus ny is the y component dotted with dou w by dou x I plus dou w by dou y j. So this is what it is, and because it is a dot product, this becomes nx dou w by dou x plus ny dou w by dou y. Okay, and this whole thing is evaluated at point P. So this is also at point P. So now we have to look at point P and then say what is the, so for this point P we can find the surface normal vector to be like this. So we have nx, so let me just for the cell 7, this is B here and A, this is point P, and so point P has this as the outward normal vector to the cell to the side AB, and this has a component of this much as nx and this much as ny. Okay. Now the gradient here is of some direction which is known from the gradients we can see, and so the cross product, the dot product of these two will give us this particular value here. So in this particular case we have an equilateral triangle. Okay, so this angle is 60 degrees and this angle is 60 degrees here, and this is our x direction and this is our y direction, and therefore this is 30 degrees and this is 60 degrees. So you can say that nx is cosine 30 degrees and ny is sine 30 degrees. So this is square root of 3 by 2 and this is equal to half. This is for point P, and ny is actually, it is not actually this is minus 30 degrees because we should be counting all the way from here, and so from that point of view this becomes minus half. So it is not 30, it is actually 330. Okay. So we always count the angle in this direction, so we can actually put this as 330 here. So in this way we have no difficulty, special difficulty in working out what nx and ny are for the point P. Now we need to get dou w by dou x at point P because we need to evaluate this. So we are writing this as nx at point P times dou w by dou x at point P plus ny at point P dou w by dou y at point P. So, each of this is being estimated from the geometry of this triangle, and the side here we evaluate nx and ny, and the gradients here are evaluated from the difference between the neighboring points. Now, if you come to this point here, this is the value of this is 7th cell and this is 8th cell, and we can say that the gradient here dou w by dou x at P can be written as W7 minus W8 divided by XC7 minus XC8, where W7 is the value of the velocity for the cell 7, and this is the value of the velocity for cell 8, that is delta W, and this change is happening over a x distance of, as you move from here to here, the x displacement is the difference between the x coordinates of the 2 points. So, XC7 minus XC8. We said right in the beginning that the centroid of each cell needs to be worked out. It is assumed to be known, and therefore we know these values here. So, similarly we can write down dou w by dou p, dou x, dou y at point P as W7 minus W8 divided by YC7 minus YC8. We need to keep in mind that the same order will also appear here, W7 minus W8 and XC7 minus XC8. We cannot say that XC8 minus XC7. So, if you put here 8 and 7, then it is again 8 and 7 like this. So, that is how we can evaluate this, and using this we can write this down here as square root of 3 by 2 times W7 minus W8 divided by XC7 minus XC8 minus 1/2 of W7 minus W8 divided by YC7 minus YC8. So, this is our n dot delta gradient of W at point P, and this has to be multiplied by the length here LAB. Okay. So, we can take small a to be the length of the cell side, okay, because we have chosen an equilateral triangle. This is side length A and A like that. So, we can just take that value here, and therefore, the evaluation of this particular term here, this particular term will now be given as square root of 3 by 2 times W7 minus W8 divided by XC7 minus XC8 minus 1/2 of W7 times A. Okay. We similarly evaluate this quantity over cell side B, BC, and this quantity over cell side CA here, and then we can work it out. We can add all the three, and we put that equal to C times area of the cell. Okay. So, let us just do that, and we can already see that the evaluation of this term has given us, has introduced the values of W7 and W8 and the coordinates. So, if you look at this term here, side A is known here, and all these XC's are known and YC's are known here, and the only unknowns are W7 and W8. And So we can also bring in the whole thing, and that will give us an algebraic equation. So now let us go here to the side BC, okay, and here we said this is Q. Here we have this is Nx. So having evaluated for the side BA, let us go to side BC and we associate the midpoint as Q here, and the outward normal vector for side BC is vertical 90 degrees because side BC is horizontal as per this diagram here, and therefore for the side BC we can say that Nx is 0 and Ny is 1. And if you look at this expression here, we are multiplying Nx times dou W by dou x. If Nx is 0, it does not matter what this dou W by dou x is, we do not need to evaluate this. So we only need to evaluate Ny dou W by dou y. So we can write dou W by dou y at point Q as the value of W at 7 minus the value of W at 9, which is the immediate neighbor, upwards neighbor, divided by the distance between the two, vertical distance between the two. So we can write this as W7 minus W9 divided by YC7 minus YC9. Why we brought in YC and all this? Because it is only at the centroid we know the value of W, either at centroid of 7 and centroid of 9. Okay, so we can write it like this, and therefore n dot gradient of W at Q times LBC will be equal to W7 minus W9 divided by YC7 minus YC9 times A, where A is the length of the side BC. Now we come to side CA here. Again we put the centroid center of this face at R, and this has an outward normal vector like this. So this has Nx and Ny, and this is again 30 degrees. So it is actually 210 degrees. And so for side CA we can say that Nx is equal to minus square root of 3 by 2 and Ny is equal to minus 1 by half. Okay. You find out what the angle is and then you substitute in the cosine theta, and then you should be able to get this. And now we need to get dou W by dou x at R can again be written as W7 minus W6 divided by the horizontal distance between the two. So we can write this as W7 minus W6 divided by XC7 minus XC6, and dou W by dou y at R can be written as W7 minus W6 divided by YC7 minus YC6. So n dot gradient of W for R times LCA can be written as square root of 3 by 2 times W7 minus W6 divided by XC7 minus XC6. There is a minus here, minus half times W7 minus W6 divided by YC7 minus YC6, and this whole thing times A. So we can add this part and this part and this part and set that equal to C times area of the cell, and that will give us the evaluation of this partial differential equation over the cell 7. And we can see that when we do that, what we have is an equation of this plus this plus this equal to C times area, where C is a constant and area of the cell is known here, and the coordinates are all known and those are numbers. So, we have those become the coefficients of W7, W8 and all that. So, that will give us a linear equation involving W7, W8, W9 and W6. So, the node itself and the 3 immediate nodes which are surrounding it, and that becomes an algebraic equation for this particular cell. And we do that for every cell, and from that we can get 9 equations, 9 algebraic equations, and we need to solve all the 9 together, obviously, because this equation cannot be solved on its own, because we need to have W6 and W8 and all that. When we solve all the 9 together, we will be getting the velocities at each of these, and from that we can get the velocity profile or velocity contours and so on. So, the way that we discretize the governing equation using the finite volume approach is a bit more complicated than what it is for finite difference formula. In the case of finite difference, we directly substituted the finite difference expression here and we immediately got it, whereas here we have to evaluate the direction cosine of each of the faces and then the gradient at each of the faces and then go through all this derivation. But the advantage of this finite volume approach, this particular approach, is that it can be applied to cell of any shape, whereas the finite difference approximation for this can be applied only on a structured grid where the grid points are at the intersections of lines of constant coordinate curves. Okay. So, that is a disadvantage with the finite difference method, but if you can use finite difference method, the discretization of the governing equation at any point is pretty straightforward. In the case of finite volume method, it is much more tedious, but it can be done. So, we will follow this up with a tutorial in which we will go back to this thing, the same triangle, and derive all the 9 equations using this particular approach, and at the end of that we will have 9 equations for the 9 variables which we can solve.